Well, good afternoon, everybody. Thank you for the invitation to this meeting. This is the second time I present in this seminar series, so I thought I would talk a bit more detail on one particular research that we were working on, which is on the piezoresistivity modeling of carbon nanotube polymer composite sensors. My name is Kawai. I'm in the mechanical and aerospace engineering. So a little bit of background before I go into the topic. I'm an aerospace engineer. I got my doctoral degree at Caltech and joined UCF 2017. So it's been a very exciting 5-6 years. Working on several different areas. My home field is mechanics, mechanics of structures, materials. Particularly, I think about structures that can change shape, dramatically, and we have applications that are focused on space and aircraft structures. We want to make structures that are not static, but they can deploy, they can be packaged, they can probably morph into different operational shapes to gain different benefits from the geometry change. And also another area that we like to work on is lightweight multifunctional structures. So not just the geometry of materials and structures that we look at, but then there are functional behavior as well, right? So there are for example thermal radiation, things like sensing, and also light absorption type of materials and structures that we want to incorporate in a very efficient way is really how biological materials and structures behave in nature, and that's kind of the inspiration that we draw on is this material structures that happen in nature. Another area that we're starting to go into is in space manufacturing. A lot of these materials that coming out from research and advances, and they can be they provide a lot of benefits, and then can solve a lot of logistical problems and change our mindset. We'll talk about a little bit about that, at the very end. So I teach some classes related to solid mechanics, and there are some awards that I fortunately have obtained in the past. So, some research for us that I'm focused on at the moment, as I said, the core of our research is, founded on mechanics. At my core is, about mechanics, and how these things change geometry, how to change the microstructures, and, how to design architectures at a different scale. How to combine them on a very thin structure so we can, become flexible and change geometry. How the material properties change over time, and all these things are important. If you look at aerospace applications, because they're typically very long-term applications, they're typically autonomous. You don't want to surface them because they are supposed to work on them itself, right? So they are kind of operate in these remote areas. Right, so a few research for us, we're working on an ONR project with an ONR project on the deployable propeller. As we have a lot of work on deployable spacecraft, mostly funded from NASA, and a little bit from NSF, and also another work that we've been working with NASA a lot is making huge balloons that go to the atmosphere, upper atmosphere. And the last, in space manufacturing, we want to propose a new concept of creating these structures and sending structures to space, and that's an exciting area that we are getting into. So let's go back to today's topic, which is strength sensing. So I want to talk about this topic because it actually comes up quite often when we try to design structures. And what we don't have is that we don't know how the structure is performing when it's in operation. And it's very difficult to use traditional sensors on lightweight and flexible structures because they're not stretchable. Typically, they're not bendable. They are, let's look at, for example, just common metallic sensors. They're not lightweight, and they typically don't have a very high strain limit. So they start to have a different sort of behavior, as we go on to more than a percent strain. They're pretty good at long-term stability, the traditional ones. So we're looking for some new solutions that are more, appropriate for this type of application. I can, kind of go through that. The challenges, I'll just highlight that one example that we work on, super pressure balloon. So these are the sensors they actually put on this, a huge balloon is basically a plastic envelope. It's just the same material you use in your plastic bags, in polyethylene. But this is very thin. The sensors they put on, they have to put on it because it's supposed to go on for, 3 months or more, 6 months just by itself in the atmosphere. These are very intrusive sensors they put on the balloon to kind of monitor its structural health. And these, they are not bendable, they're pretty thick. And these ones, they often don't get, the balloons keep failing, and these sensors are really not helping much. And there are other places that we would like to put these sensors on. These are structures that, typically, very flexible, adaptive aircraft, deployable spacecraft, and obviously motion detection is another area that can be used. They can take advantage of that. Now, we're looking at carbon nanotube paper as the strain sensors because there's some nice characteristics with it because it's pretty stretchable. Well, when it's embedded in polymer compliant substrates. So itself is pretty brittle. But if you embed it on a polymer substrate, it kind of follows the property of that substrate. So it's kind of nice because you can embed it on many different many different structures without changing the property of the structure, which is a big problem for lightweight and flexible structures. You put something stiff onto it, you're actually changing it, you're not measuring it. And this paper has a piezoresistivity, which really is just a change in the electrical resistance as you apply mechanical strain. So it's shown on here in the figure on the right, an experiment just showing the behavior, right? You have typical sensor graph, right? You have the resistance change of some corresponding to some mechanical strain. This carbon nanotubes is a network of carbon nanotubes is conductive material. So we want to understand really how to design these sensors and what is this network structure, because most of the time when we look at the literature, there are a lot of sensors based on carbon nanotubes, but the mechanism is actually not very clear because there's no really predictive model that allows us to kind of navigate the design space. So fundamentally, there are kind of nanoscale tunneling resistance that is governing the property of the conduction. So in the literature, most of the time, so we look at the separation distance. So if you have two CNTs that are in vicinity, they actually can conduct because the electron actually tunnel through the space between them. So they're not touching, but they can conduct by this electron tunneling, and that behavior is fundamentally based on the distance. And that's all fine. And we have been modeling this with this equation down here. But a lot of that, the characteristics of the CNT are missing. So this is just taking the distance between them. So what we found out is that one has to really introduce the chirality of the CNTs to actually get that, tunneling resistance correctly. So what we've, introduced into this type of nanoscale model is, the atomic registry. So the CNTs have to align because of the structure of the chiral structure of the CNTs. The probability of that tunneling resistance based on whether they are actually aligned. So this is kind of two pictures, right? So you have two CNTs and the structure of the carbon atoms, they align here. And so it gets to maximum tunneling conductivity. But on the other side, if they are not, then you get drastically reduced tunneling resistance. And that is, something that has been, experimentally found out. So there are, nanoscale experiments and also, quantum level simulations to prove that, when you have two CNTs interacting, that angle matters a lot. And so this is what we've done. So the blue graph is what we have introduced in this atomic registry, and the amount of area overlap between two CNTs. So this is a comparison with an experimental study done in the literature. So that is, kind of alignment angle. So how these two CNTs are kind of, changing the alignment. So that was pretty promising for us, to be able to capture that. So there is another issue with this, is that the amount of area overlap is a geometric parameter. So it's not just the registry between CNTs, because the CNTs are finite sized, and then there's an area overlap that is also a finite parameter that has to be taken into account. And that is what we have shown here, that we can also capture that with our current model. So I just want to highlight the yellow one. The yellow line here down here is basically what the model in the literature has always done. So there's no sort of that the registry dependence on the model. Now, we want to look at real sensors, so that requires us to go actually one more scale up to the microscale. And then so that's what we look at in terms of modern perspective. We have a network of these CNTs, distributed along the polymers. And we have developed a electromechanical model that have this nanoscale tunneling resistance that we apply on a finite element simulation. But the nanoscale, we apply the atomic registry and resistance model that we developed. And so this part is interesting outcome from this is that if we do compare the computational model that we have developed, this is dual scale model, so we have to do something in the nano tunneling resistance. And as you stretch the material, so the network all changes. So the kinematics and deformation all change positions, the distances changes, the alignment changes, and all that have to be taken into account. And we found that, once you do that, the network becomes a lot more sensitive, because all these dependence are not just on the distance, but, on all the morphology of the network. And so we have a more, accurate description of the actual network deformation. And so this is what is shown here. The blue line is the new model that we proposed. The orange line is what the literature, behavior is always predicted. And the square, the triangles are the data. And you see that the sensitivity has to be there. The sensitivity, is not correct if you don't put in those resistance at the nanoscale correctly. So this is a work that we want to put forward because we have a good designed framework for our nanotube paper. And we want to make use of that, electrical conductivity and the tunable electrical conductivity of the paper, and look at a different problem, which is really manufacturing composite structures. So the general goal here is we want to bring down, logistical footprint of large structures. Typically, they are made on Earth, and so this is, you need huge upfronts to make them. But this is not a viable route for, a space future. So we are thinking to, developing in that area a CNT paper-based, material-based manufacturing route where we can kind of combine that, electrical heating of the CNT paper onto composite material feedstock. So we can bring large rows of these solid materials and do those, manufacturing in space. So I think the time is up, but thank you for listening. That's all I have.